Haystack Observatory. He got his bachelor's degree in space physics in 1987 from Peking University and a PhD in space physics in 1995 from the Chinese Academy of Science, Wuhan Institute of Physics. He has been a research professor, research associate, and a postdoc researcher while working at that institute for 10 years, at Kyoto University for 2 years, and Boston University for 2 years, before joining MIT in 2001. Dr. Zhang conducts a broad spectrum of ionospheric research, covering both observational and modeling aspects. The current focus is subauroral dynamics and ionosphere-thermosphere magnetosphere coupling, particularly during geospace storm periods, as well as traveling ionospheric disturbances, ionospheric climate and variability. So today, Dr. Zhang will talk about ionosphere disturbance in response to transit solar irradiance events. Rong, please go ahead and start.
Okay, thanks very much, Nin, for your invitation and introduction. So this is actually my second time giving a seminar at HAO. The first time was in, I think, about 10 years ago, 2010. At that time, I was talking about the ionospheric variability and the long-term changes, long-term trends. So it took us 10 years. Actually, early this year, Wenbin, Nin, and myself had a joint proposal submitted to LWS, and lucky enough, we were selected. So it took 10 years for us to really get together with a good proposal, and now we start a collaboration on this long-term trend topic. Well, it's amazing. After 10 years, we're still interested in this topic. But after my today's presentation, I hope it won't take another 10 years before we can get another collaborative project. So I hope we continue collaboration on topics including what I'm talking about today, which is the ionospheric disturbances associated with transient solar radiation changes. So my definition about this transient ionospheric changes includes basically three things: solar eclipse, and then solar flare, and the solar terminator. You know, the solar eclipse occurs with ionospheric solar radiation reduction, significant reduction. And the solar flare comes with enhancement in this photoionization and many things. And the solar terminator is somehow similar with the sunrise, southern sunrise, increasing the ionospheric photoionization and so on. So there are some similarities among these phenomena. So, and this has been actually studied by many people for many years. So I'm trying to provide some new insights into the physics associated with those ionospheric disturbances, particularly traveling ionospheric disturbances. So just a little bit of introduction about the technique. So I am an ionospheric guy, mostly working with observational data. So recent years, we have been developing algorithm to calculate the differential TEC, and it's based on our global GNSS TEC observation. So far, we have around 6,000 receivers. And these receivers looking at the GPS or GLONASS, and at some point in the future, this is what we are planning to do, is to include the Chinese Beidou satellite as well. So hopefully it won't take too much time. But so this is a really useful technique to study the global ionospheric disturbances. What you see here on the screen is 6,000 receivers. But each of these receivers, looking at 6 or 7 different GPS satellites, or the same amount of GLONASS satellites. So the actual coverage and the resolution would be And it's 10 times better than what you see here on the screen, which are just the receiver locations. So the spatial coverage will be much better than this. So since 2017, we are producing the differential TEC, calculate the so-called ionospheric disturbances. Before that, we have data mostly for storm time. So if you are interested in any of these, we are really happy to provide this differential TEC data to you. So the way we calculate this differential TEC is basically detrend the background ionospheric variation using, what is that? Sorry. Okay, so using the so-called Savinsky-Golay low-pass filter. That filter is not fancy at all. I mean, it's very much similar to sliding window. And you can select the length of the window. So, so what you see here on the top is the observed total electron content by a single receiver at this location, looking at one particular satellite, PRN21. So you can see the observation is typically about 4 or 5 hours for each receiver looking at one satellite. And this particular example was at a higher latitude where you can see in our original data the fluctuating TEC. But the way we calculate differential TEC was to remove the background variation. So with this red curve, and the black curve is the differential, which is the difference between the two curves. So this is an example showing how we do this. So one of the key components here is the length of the window, because it will determine the kind of waves you can detect. And most of the times we use 1 hour or 30 minutes. During some of the events, for example, solar eclipse, we sometimes using 2 hours. I will talk a little bit about that later. Here's another example at mid-latitudes, subauroral latitudes, where you see the blue curve is the original TEC, x function of time, and the bottom panel is the location, the Pierce point. So here you see this is the trough region, mid-latitude trough region, where the density is lower. And to the left is the equatorial wall of the trough where the density is higher. So on top of this, you can see there are many ionospheric disturbances indicated by this black curve. Another example I think I need to emphasize probably, this is the solar flare observation. So somewhere around the 12 UT, the differential TEC suddenly jump to this point. And the way we calculate the background trend shows the red curve here, and that runs smoothly through this region. So that actually before the peak of the flare, you have a negative. This is just because the background is too high. And then after that, you have a positive. So this is a well-known feature of this kind of running window. When you see a large enhancement, typically you can have a negative value before that. So this is for flare condition, and this one is for the solar eclipse. The red curve is the anticipated electron density reduction, and the dashed line is the level that we determine with that filter. So if you see one TEC deviation from the reference line, the actually electron density depreciation is actually 2 TCU if we count from the starting point. So yeah, it's the difference from this point to this point that is the actually ionospheric changes. That is the same case here. So for this particular flare, you have a negative here minus 0.8 TCU before the peak, and after that you have positive. So the total changing is actually 1.6 TC unit for this particular flare. And then let me talk about science. So this was from the 2017 solar eclipse. This was really amazing event where we have really good observational coverage over the continental US. So on the left is a 2-hour window. You basically remove the background variation with this 2-hour window. The reason why we use the 2-hour window is that at any given location, the length of the eclipse is about 2 hours. So you basically remove this 2-hour variation. And you see the scale goes from +1 to -1. And that means the actual depletion by the eclipse is probably about 2 TCU rather than 1 TCU, as I explained earlier. But what's most interesting is probably on the right is our 30-minute sliding window results, the differential from this 30-minute window, showing really fine traveling ionic disturbances structures. And let me pause at this time, maybe now. Yeah, so at this moment, you can see clearly the so-called bow-shaped traveling ionic disturbances. And this kind of TID moving along with the eclipse shadow and westward. So in the westward direction, they are not exactly at the totality center, but it's a little bit behind that, behind the totality. So I also want to mention that another factor associated with the terminal waves, that is also because of the reduction of changing of the solar radiation. So at the sunrise terminate, we often see eastward traveling ionic disturbances. At sunset, we see the westward. And here, what you see here is a little bit, is clearly westward propagating wave. So this is zonal propagation. And the shape of this bow-shaped TID is evolving in time. And so at this moment, so the pattern actually goes into the reshaped pattern. And so from this, we can also looking at the wave properties, including the wavelength and periodicities and propagation speed. And this is the next slide. So in this slide, we show the kilogram of the differential TEC as a function of longitude. Here on the top was looking at about 40-degree latitude. And so this is longitude and universal time. So this pattern here, the signature of the bow-shaped ionospheric disturbances, and you can estimate the speed based on the slope. So this slope is actually 150 meters per second, and you can measure the distance between the two fronts. So this is about 2 degrees in longitude, or 270 kilometers in distance, 25 minutes periodicity. So what caused this? Potentially there are two possibilities. And first is of course what people called the bow wave, and Chomness in 1970 published his paper on this. This was a really preliminary results. In his calculation, the sun, the moon is over here, and the shadow is behind that. So, and he also predicted a number of properties in the thermospheric altitudes. But I should point out that, so by the way, so this pattern is reshaped. I think this is very important. The thermospheric results of this study was really, really simple, really rough estimation. The model he was using was isothermal atmosphere. So that means the temperature does not changing from the mesosphere all the way to the thermosphere. So but the basic physics is very clear. Here, assuming the ozone layer, the solar radiation associated with the solar radiation changing the absorption of the solar energy by the ozone, so that rapid sweeping through the atmosphere and producing the bow wave. But how the bow wave exactly look like in the thermosphere is not known at all, even though he predicted something, but I don't believe that is physical at all. So our observation basically is saying that we see TID, we see the pattern is evolving, but initially it's more like concentric type of waves, but later on they are more like V-shaped. Another possibility is the in situ excitation of the ionospheric waves within the ionosphere and the thermosphere. So there were simulations using GitHub indicating the possibility of thermospheric ionospheric disturbances right after eclipse. So we still need more observation to really confirm the source region of those ionospheric disturbances. This is a side story just to show you some of our most recent study indicating the potential conjugate effect in total electron content for the same solar eclipse. So on the top is, so this left panel again is a 2-hour running window detrended results. Top is the same as the one I showed you earlier, but bottom is the southern hemisphere. It's interesting that the depletion occurred at the time when the north is under moon shadow. So on the right is actually latitudinal cuts as a function of universal time. So in the north, you see the progression of the depression southward. And in the southern hemisphere, earlier, you see the depression occurred at higher southern latitudes and then moving toward the equator, sort of conjugate to the pattern in the northern hemisphere. So that is quite interesting observation. We proposed something associated with the plasma pressure gradient reduction around the flux tube. But that's a different story. I don't want to spend more time on this. So solar flare. So Ning has a number of papers discussing about the solar flare produced ionospheric and thermospheric changes. One of the paper was on this September 2017 event. This event had quite a lot of disturbance periods with X level of solar flare. One of the points in this paper was that the large-scale TADs and large-scale TIDs are unlikely produced by the solar flares. So, so Ning, correct me if I'm wrong about that. But the flares can actually amplify some of the existing waves. So Ning has been focused on these large-scale TIDs. So we had an observation as well in the GPS data in this time period. So we're looking at TIDs, particularly those medium-scale TIDs. But the way we, next slide, yeah. So next slide shows just a little bit about these solar flare produced ionospheric disturbances. We have a really sensitive technology, which is the GPS, to detect, to monitor the flare-produced ionospheric operations. So the bottom panel is, again, the same as from Ning's paper showing the X-ray flux as a function of time over these 6 days. And top is our differential TEC from the 30-minute sliding window results. as a function of longitude and time. So this is basically looking at a mid-latitude, latitude, 40 degrees latitude, and then around the global from positive 90 degrees in Asia to Europe and then to American sector. So the data set is basically here. You can see a curve, a solid line. That is the sunrise terminator. And then there's another one, is sunset terminator. And between them is the day side. So, and then you can see for this X-class flare, there's immediate ionosphere changes. It's a very nice one-to-one correspondence between the differential TEC and the X-ray data. So this X 1.3 is relatively smaller. You're still able to see it's vertical lines. And then this one is probably M-class flare. You can see that. And this one here too, on this side, obviously. And this one, there are a lot of things here, so I cannot identify which one is the flare produced. And then this one here, I believe is M-class flare. You can see this vertical line. And this one, you can see this. So I'm really interested in this M-class flare. And this is the, it's sort of zooming in over 3 days, but shows the latitudinal variation in European sector and American sector. So basically, what I'm trying to say is this is M7.3 flare. You see this. Obviously, 1.3x, this is large, and 8.1. And even this M3.7, which is really small, you can see the ionospheric responses. So this is quite a sensitive technology and providing monitoring of the solar flare produced the ionospheric disturbances. That's another side story because I know Nin and Jin Liu and others have been working on this particular flare, looking at lower and equatorial latitude ionospheric disturbances produced by the flare because of the enhanced conductivity. So the electric fields tends to be reduced. What happens at the mid-latitude here is quite different. And this is our observation at Millstone Hill. On the right is the vertical ion velocity, and different colors are different altitudes. So at the peak of the flare, you see a large vertical drift upward, and that upward velocity increase as a function of height. And the magnitude of this vertical upward drift could be up to 80 meters per second, which is quite significant. Then so this is the peak of the flare, and the enhancement actually decayed in 30 minutes. So at this point in here, this is significant, reduced back to the normal condition. So there is about 30 minutes lifetime. And this is corresponding ionospheric density variations in NMF2, the F2 peak density, and the F1 peak density. So the F1 peak density enhanced by 30%, and the F2 enhanced by 20%. So this is our very accurate plasma line measurements. So the effect actually decayed in 30 minutes as well, corresponding to this decay in the vertical velocity very well. And this was another event, 2005, September 7th. What happens, I want to show you is the altitudinal profile. So the flow time, you see the enhanced electron density in the F region. And you also see the electron temperature enhancement. And then this is the upward ion velocity that I talked about earlier. And it's trying to understand this. I think Jin Liu and his student had a simulation indicating that ambipolar diffusion velocity could be very important because of the enhanced plasma pressure due to density enhancement and temperature enhancement. So that is really a possibility. But I don't know whether there are other things, whether there will be electrodynamics associated with that. I really want to see whether you guys can looking at potential electrodynamics. Let's back to the TID study. How much time? 27. So back to the TID. I showed you this slide earlier, but this was the original TEC data. The blue curve again is the original TEC, and the red curve is our reference, and then the black curve is the difference between them. So at this particular location, you can see that before the flare, the actually ionosphere is really very quiet at this location. But after that, you can see clearly oscillations with periodicity about 30 minutes or slightly less than that. And then this slide is, this panel is from a nearby location. Again, before the flare, there was small amplitude ionospheric disturbances. And after that, you have clearly organized large amplitude disturbances. So, these disturbances were newly excited by the flare, were amplification effect by the flare. So this is actually a question. And I'm trying to address this with these maps. This shows differential TEC maps at different times. The flare peak was about 12:02. And so this was 8 minutes after the peak of the flare. You can see the organized, the pattern, the wave front, with a distance about 1 to 2 degrees in longitude. And so this is 12:10, and this is 12:11. You are still able to see this. And 12:13 here. And 12:18, 5 minutes later, the amplitude has been decreasing time, but you're still able to see this. I want to draw your attention to the fact that this wave front is not far from the terminator. So obviously this side was affected by the flare, and this was the light side without the flare impact. But this wave front is really close to the terminator. So these are the data from other times on the same day. So this was before the flare, where in the East Coast you have some sort of disturbances. This is 7 minutes after the peak of the flare, you have disturbances. At the same time, in the East Coast, you have the terminate produced TIDs like that. And this is 1 hour after the peak of flare. These wavefronts I showed earlier, still there. And this is 15. So that's 3 hours, 4 hours after the flare peak. This become completely rotated more in the horizontal orientation, so not like the wavefront in the Mariana direction. And this in California area is most likely produced by the sunrise terminator. So this is just for comparison to a day before. So exact the same time, 12:10. And you can see some of the disturbances in the Florida area, but not very close to the terminator. It's probably at least 1 hour away from that. Not the same location as compared to the flare day. So this is our way to look at how the things propagate in time. So kilogram, what you see here is the kilogram showing the differential TEC as a function of longitude and universal time for the 2 days, the fifth, which was quiet before the quiet here. But actually there was another flare on the same day. anyway, so on the 6th, this is a flare produced the electron density enhancement, and the blue area is the terminator, the sunrise terminator, and the flare effect obviously on the day side. So the effect probably can extend all the way to minus 105 degree longitude, which is actually at Boulder. But what's interesting is that, let's look at a long flare day. You can see a lot of waves. They are propagating apparently eastward. And what's interesting is, so terminator is here, but you start to see these waves about 1 hour later. It's not exactly at the time of the flare, but it's 1 hour afterwards, approximately. But on the flare there, you can clearly see first the ionospheric responses within 30 minutes. And immediately after the flare, you see this west-eastward propagating pattern, and started actually at the edge of the flare. So what's interesting is to compare this so-called triangle area. In this triangle area is formed by this 12 UT and this local time, and this 105 longitude. Well, we did not see significant terminated waves, but on the flare day, right after flare, you have these disturbances propagating eastward. That is actually the pattern here associated with that. So yeah, another thing interesting. Yesterday, I talked with Wenbing about what he called the intrinsic oscillation in the thermosphere and the ionosphere system. And what you see here, this is obviously the flare produced ionospheric density, but about 1 hour, in about 1 hour, there's another enhancement, and then maybe a little bit later, weaker, but about 1 hour again. So and that is interesting. That is definitely not produced by the solar wind penetration or something like that, because this was a relatively quiet period. And on this day, you can also say this. About 1 hour later, there's another coherent enhancement. So that is interesting. We don't know why, but observationally, I see this in these 2 days, but also other days, while the electron density coherent enhancement occurred about then later, 1 hour afterwards, after the flare. And it has also multiple oscillations. So that is something we don't know, we don't understand. This is a short summary of the findings associated with these post-flare TIDs. First, they are horizontal. They have horizontal wavelengths about 200 to 300 kilometers, meaning about 2 to 3 degrees in longitude. And they are eastward into dayside, and with a speed pretty slow, 150 meters per second. And most of these occur near the terminator. And then the question is, are these TIDs are enhanced version of sunrise effect in exciting terminator waves? We know terminator waves can be excited by the sunrise effect. The UV enhancement associated with the flare can produce an enhanced version of these terminator waves. Is that possible? But another explanation may be that they are just the regular terminator waves, but amplified by the flare. So based on the results I showed earlier, I tend to believe this possibility, which is the enhanced solar flare probably produce a new version, an enhanced version of sunrise effect in exciting terminator waves. And the fundamental question here is because all these TIDs I see has a significant zonal propagation. Now the question is here. So there was a paper by C.H. Liu and Casey Yan. They both are very well-known gravity wave experts. And in their paper in 1969, so they studied a scenario where basically you have a zonal propagating gravity wave, but the plasma does not allow to move across the field lines. Plasma only allowed to move along field lines. And there's results indicating that the gravity wave will be significant attenuated because the plasma ion drag effect along the field line is huge. Plasma does not allow to run across the field line, so that the gravity wave will be significantly small in terms of the amplitudes. But in observation, this is not really the case. We as I see here, there are many TIDs that propagate in a zonal direction. We don't see the gravity wave significantly damped, significantly attenuated. Why is that? So I think this will involve the electrodynamics. That is my next topic. So the question, as I said, is I just using this plot to indicate that there are significant zonally propagating the ionistic waves. So we have looked at two locations using our 2 years of daily TEC, differential TEC data. That's a lot of data. So two locations, one is at Millstone Hill location, the other is in the West Coast near San Francisco area. So this is the West Coast and East Coast difference. And we detect the TIDs and we calculate their propagation direction. So this is just a comparison. If we look at here in the East Coast, so 08 local time is this cyan curve, but look at the distribution here. So there's a significant amount of propagation in the southeast direction. So the azimuth angle is 135. That means this is southeastward propagating at sunrise time and after sunrise time. So there is a very significant component southwest propagating in the morning and local noon time. But in the afternoon, 20 and 24 midnight, the waves actually westward, southwestward. So the azimuth angle is about 225. So this is quite different. But my point is, this zonally propagating TID is, there are so many these kind of cases. They are very frequent observed in our differential TEC data. So point is why we still have this strongly zonal propagating TIDs, given the fact that the magnetic field will somehow prevent the zonally propagated TIDs. So there must be electric fields involved that driving this zonal propagation. So we designed experiments, a number of experiments to look at the electrodynamics associated with the sunrise terminated wave or zonally propagating waves. So the experiment was relatively straightforward. We have two antennas. The zenith antenna obviously looking upward, and the MESA is turned to the eastward direction with about 67 elevation. So with this configuration, the averaging altitude 300 kilometers is basically 100 kilometers away between these 2 points. So with this configuration, we can estimate the ion velocity in the zonal direction. So that's what I call the V east. That east direction, east velocity is apparently associated with the Mariana electric fields, right? E cross B. So then we can estimate this. We can also estimate the zonal propagation because you can measure electron density at this point and at this point, and we can correlate it between the observation from here to here, and to calculate the lag time, the propagation time in the zonal direction. So this is what we have. This is one of the experiments we did September 4th, 2018. This is our plasma line electron density on the two antennas. The blue curve is the vertical antenna, zenith antenna. The red curve is the MISE antenna. So notice that the sunrise is on this side, so that local sunrise on the MISA would occur earlier than the zenith antenna, because this is the east side, right? So, but what you see here is actually the disturbance phase occurred earlier on the zenith antenna, and the MISA antenna, which is looking to the east, had a later phase than this. So this is very consistent for many hours. And we calculated the delay time between these two series of trains. And the delay time was about 10 minutes. So then we can figure out the propagation speed and the periodicity. We can look at this wavelet analysis, about 30 minutes, 60 minutes or something like that. And obviously we have GPS. That GPS data shows this differential TEC as a function of longitude and universal time. I showed this kind of plot many times. But you can see clearly these are the eastward propagating TIDs into the eastward direction, into the ocean area. And we can compare the slope to calculate the zonal velocity to the ISR measured zonal velocity. So they are quite consistent. Their velocity is about 150 meters per second, something like that. And these are the maps of the differential TEC at this time, 11 local UT. It's probably somewhere over here. So you can see some of these wavefronts here. They are basically along the Mariana direction, along the magnetic field line. So, so these are the terminated waves associated with this sunrise. But after that, so this is about 16 UT here. The wave actually rotated to more in the horizontal direction, more in the zonal direction. So this is a rotation from the Mariana to this direction. And obviously we have electron density by the vertical antenna. So you can see this is electron density as a function of height and universal time. And this is again, the differential electron density removed background variation determined by the 2-hour window. So you can see this is very nice. There is very nice gravity wave features with downward phase propagation with height. So we can even estimate vertical wavelengths, which was about 70 kilometers. So this is quite beautiful gravity wave signatures. And then we also have these vertical measurements, vertical velocity here. Before sunrise, night side, and there was significant downward, and after that is significant upward. And this upward may be very similar to the so-called pre-reverse enhancement at the equatorial latitudes. People have been looking at that these days, and there are papers looking at the morning hours electron, the vertical upward velocity right after sunrise. I think Joe has and his students has paper on this. I think this is similar to that. Anyway, so this is the vertical velocity. They have sort of quasi-periodical oscillations. And the vertical one is the key of this experiment, which is the zonal ion velocity, east-westward ion velocity, or the equatorial electric fields. Again, positive, negative, negative. So they are quite periodical. And they are also sort of well correlated to the vertical velocity as well. So that is really interesting. The bottom panel here is the zonal velocity V east, same as this guy here, but looking at the two different altitudes. And this one is the altitude around 300 kilometers. 300 kilometers here is in the top side, because in this case, the sunrise F2 peak is about 220 kilometers or something like that. So 300 is well above the peak. So this is 300. And the bottom is the below the F2 peak. I think, yeah, here, this is about 174 to 184. So that's about 170 kilometer altitudes, bottom side and top side. What you see here is the very interesting feature where the phase of these oscillations are opposite. You see a positive here, low altitudes, and a negative here, and high altitudes in top side. And there's a very well one-to-one correspondence between these oscillations. So if you put this zonal velocity with the vertical velocity together, so you have upward, westward, and eastward and downward. So the actual vector would look like this. So this vector form what they call the vortex. So the vortex has been observed at the equatorial latitudes right after sunset, probably around the PRE time. And our observations show some similarity with this. So this is another, let me take a look at time. So this is another event. I don't want to say anymore, but this is my final slide. So this slide discusses about potential physics. So the mid panel here, basically you're looking to the north and your left, west, east, and your right. So you have gravity wave produced the zonal wind disturbances in the westward direction. It produced the U cross B Peterson flow in the F region. And because of discontinuity in the conductance, so then there's a separation of charges, positive charges here and negative charges here. So that produces the polarization electric fields in this direction. And then it produces westward ion velocity. So the bottom side and top side has different polarity of the charges. So that here you have opposite ion velocity to the velocity in the F region here. So, and then if the wind switched the direction, you got the opposite thing. And based on the curve-free electric field assumption, you can have this vertical ion velocity in different directions between high and low altitudes. So the point is that these terminated waves, even though they are very similar to the gravity waves in terms of the phase progression and periodicity and all those things, but they are electrified. So they are there are polarization electric fields involved in that. Now, in order really to understand this terminated wave, I think you definitely need to consider the electrodynamics. So that is my main message to you. So I made a big circle to discuss from solar eclipse to solar flare to solar terminator. The main point are here. So TIDs associated with transient solar radiation changes have been often observed. So in these different conditions. And many of these TIDs are of medium scales with typical horizontal wavelengths about 200 to 300 kilometers and periods about 30 to 60 minutes. And some of them have evident zonal propagation component at 100 to 200 meter per second phase speed. So the physics of these zonal propagating TIDs involve electrodynamics, likely caused by the neutral wind, gravity wave neutral wind dynamo action. So post-sunrise TIDs have gravity wave characteristics, propagating vertically and zonally, but they are not simply a manifestation of gravity waves. They are electrofired, and the polarization electric field are embedded in these TIDs. And these TIDs appear as vortex flow in the vertical zonal plane. So, so that's it. Thanks so much. And it took me 53 minutes. Sorry about that.
Thanks, Chen Rong. So I think Bill has a question.
Yeah, go ahead, please.
Yeah, I wasn't actually sure I had a question, but I'll go ahead anyway. It was an accident on the raising the hand. But I do, you know, I have it's a question and a comment, maybe a comment then a question. But so the fact that there are electric fields associated with these disturbances, they're actually quite slow. But typically, whenever you modify the conductivity, it tends to launch waves going up into the magnetosphere. At short periods, you would see Alfvén waves propagating, but at these periods, it'd be more like a quasi-static variation of the, you know, of the flows on the flux tube, maybe even going into the other hemisphere. So, you know, that was a reaction I had to this. I'm kind of more focused on the magnetosphere, but the question is, are you aware of any observations of this particular phenomena extending upward? And I guess you'd have to either see it on a satellite or in the other hemisphere. You know.
Yeah, that's a great question. I think this will be our very first observation of the electric fields associated with TIDs on this side. There are studies looking at the so-called MSTID at night time, and they found the electric fields associated with those MSTIDs. And they found that these electric fields in one hemisphere can map to the conjugate hemisphere along the field line. But this observation were at mid-latitudes. So there were observations at nighttime, but the daytime after sunrise, this will be the very first observation that connects to the terminator. Terminator waves occur every day almost. So that should be a phenomenon that we can see very often in our data. We actually look at the potential conjugate effect. As you said, the electric fields can map on the field line and maybe to the conjugate hemisphere, because we are talking about mid-latitudes here. So we actually look at the conjugate point. Actually, there's one plot here from the conjugate hemisphere, but I don't want to spend too much time about that. The main point is that the conjugate hemisphere, sometimes there are disturbances, simultaneous disturbances. But because of the sunrise times between the two hemispheres could be different in different seasons, sometimes they occur close, sometimes they have a few hours separation. So the local effect and the conjugate effect are very difficult to tell from the observation. Yeah, but I think that's a great question. As I said, because this occurs often, terminator waves, maybe there are chances that we can use satellite when they go across the region to look at high altitude electron density, electron field disturbances. That's potential. Yeah.
Yeah, very interesting. Thank you. And it's something that we might be able to look for in global simulations that, couple the magnetosphere and the ionosphere. So anyway, very interesting. Thank you.
Thank you. Thank you.
I think Gang has a question.
Yeah, Sharon, yeah, nice talk. Yeah, can you back to slides 25 before this one? I would just, maybe I read, have another look at it. So you say there's a correlation between zonal drift with the electron density structure, the top panel. But when I look at it, I don't see there seems the correlation is direct one-to-one.
So yeah, what I meant was the zonal propagation and the vertical propagation, not necessarily zonal and vertical density. Not density, there is no nice correlation between them. It's a complicated physics, right?
Yeah, why that's the case? Zonal vertical, I can easily say that's to correlate, even just on the rough, because you have to project. You only measure line of sight. So that's no surprise, but I'm surprised when you say those are polarization field-driven density structure, but why there's not direct one-to-one correlation?
So when I say there is no one-to-one correlation, I meant the electron density variation and IM drift observationally it's quite typical that because ionospheric response to the dynamic changes, first it takes time, second probably there are not just vertical drift that is response, but not just the horizontal drift and the response. There are many things involved. I don't know. So you guys doing simulation, you probably can do that, looking at exactly correlation between the drifts and vertical velocity. So,
but I thought you were interpreting those structures as polarization field-driven structure.
Okay.
Did you?
So yeah, so I think there are two things. One, the gravity wave. I think the top panel shows clearly these are gravity waves. This gravity wave excite electrodynamics, and that electrodynamics will drive the velocities in two directions, in the zonal direction and in the vertical direction. So this physics here actually tells about why there's a correlation between the zonal velocity and the vertical velocity. So basically, if you assume there is neutral wind disturbances in the westward direction, you have this westward velocity in the F region, and the low altitudes will be the opposite direction. But so this westward wind produce this velocity, but this eastward wind produce velocity. And the electric field associated them are different, so that you consider the curve-free condition, you can expect that there will be another electric fields, which is in this direction produce the downward and upward velocity. So with this dynamical scenario, yes, there will be a correlation between vertical velocity and horizontal velocity. But the caveat with this is that our radar measurements, so here are electric field driven vertical upward and downward velocity. But the radar measurements is not only the electric field driven, it has also the diffusion velocity. You also have the neutral winds. So from this exact experiment, even though we see there are correlation, but we cannot directly say, okay, the electric fields in these two different directions are correlated. We don't have evidence for that.
Okay, yeah.
But we just indicating this is possible. Yeah.
Oh, yeah. So the polarization field that you pictured here, what is the top boundary, the separation between top layer and the bottom layer? Seems like you're saying that the top of the average and bottom. But usually the polarization field should not be extended to a wide range in altitude, especially on the field lines. You basically they cannot be sustainable. They only exist between the scale height, between electron scale height and the ion scale height, or the temperature.
Yeah, so this is another part of this. This one is when you're looking to the north, and this one is you're looking westward. So basically these charges are same polarity of charges on the same field lines. So this would be able to sustain because they are same charges, same polarities. But there will be a difference in terms of the electric field differential potential between this field line and these field lines. So that is the reason why we have this polarization in electric fields. In this. So some of these, you can see here, some of this difference from negative to positive is able to maintain because of this latitudinal structure, latitudinal variation here. So it's not purely altitude; it's also latitudinal variation involved.
Okay. Well. Okay. Yeah. Stop here. Thank you.
Thanks.
Wenbin, did you have a question?
Yeah, yeah, I had one, but anyway, so we had a eclipse in the northern polar region in June, and another one coming in December in southern hemisphere. Well, what do you expect that the eclipse effects going to be the same or quite different from those happening at the middle and the lower latitudes? What do you think?
Yeah, I guess you know the answer, right? So this high latitude one will be both of these eclipse in June and December will be very unique because they are in the Arctic and Antarctic region. Well, the potential is that conductivity changes could be up to 20 to 30%. I have an estimate for the June eclipse. The electron TEC changing is on the order of 20% to 30%. I think that will modify the conductance and potentially changing the convection and maybe the auroral activity. You guys have modeling about that. I like the idea. It's just a question, observationally, can you isolate the eclipse effect from other things?
Yeah, that was my question. Can you observationally separate the eclipse effect from other geophysical?
Yeah, the June one is better as compared to the upcoming December one, because December the data coverage is not as good in the Antarctica. June one was okay, but I think we see some sort of enhanced electron density fluctuations in the auroral region. We do see an enhancement a little bit after the eclipse, the maximum eclipse. But simultaneously, there was solar wind, slight solar wind disturbances. Whether this is solar wind driven or eclipse, we still don't have a clear idea about that. Still looking at data. So yeah, we probably should work together on this topic. At the very beginning, I talked about it took us 10 years to develop a proposal to study this. Maybe we don't need that much time now. We have some ideas.
Nick, can I jump in on the end of this question? What Sharon, what diagnostics, you said there was some evidence of oscillations in electron precipitation or aurora. What were you using to infer that? Yeah,
basically this differential TEC here. I show you some of the potential, the effect associated with the flares. The flare can, the differential TEC is very sensitive to to electron density variations, even though the flare are most dominant from the low altitudes, E region, F1 region. But we found that in the aurora zone, any magnetic disturbances would produce enhanced fluctuation in this differential TEC. If you look at the kilogram as a function of latitude, you can clearly tell where the aurora region is by looking at this differential TEC data. So any disturbance will enhance that differential TEC significantly. I mean, yeah, so in the eclipse, during this June solar eclipse, I see there are enhanced activity, enhanced the differential TEC, either positive or negative. So that is the observation. What's the source is the question, and that's a question for me and for Bin as well. How do we explain this? But observationally, yes, the differential TEC tells you information of aurora activities.
Okay, thanks. Got it.
Thank you. Oops.
All right, are there any other questions? If not, thank you then, Shun, Rong again.
Thank you, Nikki. Thank you, everybody. Have a nice evening. Yeah.